Okay, we have so far studied how to calculate individual capacitors. But in the real electrical circuit, we often have more than one capacitor. Most of the time we have more than one capacitor. So we need to see how we might combine capacitors to form a collection of them. And the idea is it possible to combine the capacitance of these capacitors so that you get a single equivalent capacitance? Okay. That is possible depending on how these capacitors are connected. And there are amount of common connections. There are two types. One is called a parallel connection and the other is called series connection. We're going to study them one by one. The first one we study is so-called parallel connection. And what I mean by that? Well, what I mean is that you put two capacitors connected parallel to each other, and by that I mean you take one of these two plates from each capacitor, so this plate and that plate, and we connect them to the same terminal. So this piece and that piece share the same potential. Okay, they share the same potential because they're equal to the potential at point A. Everything is linked by metal wires. Okay, and then you take the other plate from each capacitor, so this plate and that plate, and you hook them to the same terminal B. Okay, so if you look at this diagram here, you start from point A, right? And then before you reach point B, you must branch out. There's one branch here, there's another branch there. These two branches are parallel to each other, and therefore we call it a parallel connection. Okay, what I want to know is, how does one devise a single equivalent capacitor such that the capacitance of the single capacitor is equal to this combination? Okay, so I can replace both of these with a single capacitor between the same 2 points A and B and get the same exact result, same exact capacitance. Okay, how does one do that? Well, it's not that hard to do. All we have to understand is the meaning of C equivalent. Since the capacitance of this single capacitor is equivalent to this combination, that means that if I hook up this capacitor between 2 points A and B, I will get exact same capacitance, meaning that for the same amount of V, I will get the same amount of total charge Q, so that Q over V remain the same for both of these cases. Okay? Now, what is Q? Q is the charge that you place on this capacitor. Let's say this point A has a higher potential, therefore it's going to be positively charged, and this guy will be negatively charged. Okay? And let's say here the charge is Q, here the charge is negative Q. You see here, this Q is the total charge on this plate, which is linked to point A, right? To point A. But you go back to the previous case. This point A is now linked to two metallic plates, this plate and that plate. And these two plates may not carry the same amount of charge necessarily. Let's say this guy carries Q1, okay, and this guy carries Q2. They're both positive because A has a higher potential than B. How is Q related to Q1 and Q2? Well, Q is the total amount of charge on the plates linked to point A. And here, linked to point A are these two plates, Q1 and Q2. One carries charge Q1, the other plate carries charge Q2. So therefore, how much is the total charge linked to point A? Well, that would be Q1 plus Q2, right? That's Q. Isn't that true? On the other hand, you look at these are the two plates, okay? You just get negative Q1 and negative Q2, just like that, okay? And the total amount of negative charge connected to point B would be negative Q1 plus negative Q2. That's the same as negative Q, because negative Q equals negative Q1 plus negative Q2. Same formula as this. Okay, so we established the relation between Q and then Q1 plus Q2. But what about the potential difference? Well, point A and point B has a certain potential difference V between them. And that same potential difference is applied to both of these capacitors. You see that? Because this top capacitor is exposed to VA here and VB there. The difference is V. The lower capacitor, same thing happens. is exposed to VA here and a VB there. The difference is again V. So both of these will share the same exact amount of potential difference. That is the signature of connecting everything in parallel. They will share the same potential difference. Okay, so question is, how does one find C equivalent based on C1 and C2? Well, we have to understand the meaning of C equivalent and the meaning of C1 and C2. You know, C1 is defined as what? Q1 over V, right? Actually, Q1 over V1, but V1 is just V, okay? It's a potential difference between these two. C2 is defined as Q over Q2 over V. The same V, okay? They have the same potential difference, right? What about C equivalent? C equivalent, you see, we have a Q here, negative Q here, exposed to the potential difference V, and therefore that's just Q over V. It's Q over V. Okay, but wait a second. Q equals Q1 plus Q2, right? So I can rewrite this, okay? I can rewrite this as what? Q1 plus Q2 over V. So this is Q1 over V plus Q2 over V, right? Q1 over V plus Q2 over V. But wait a second, what is Q1 over V anyway? Isn't that C1? Hey, what about Q2 over V? That's just C2. So it's just C1 plus C2. See how simple that is? Okay, so C equivalent equals C1 plus C2. If I have two capacitors connected in parallel. Okay, now does this make sense? We derived it, but can we understand it qualitatively? Well, yes, we can. Let's look at how we can understand qualitatively. For simplicity, let's say these two guys have the same gap. Okay, so this D and that D are the same. If you only have one such capacitor without the other branch, the area here will be just A1, right? So what happens if you add another branch? Well, now the charge will have two places to go. Part of it goes to the top capacitor, part of it goes to the lower capacitor, and it's equivalent as increasing the area from A1 to A1 plus A2, because this, you know, this plate has area A1, that plate is area A2. They're both connected to the same supply of positive charge, and therefore the area isn't that increased to A1 plus A2. Okay, but remember, for a parallel plate capacitor, C equals epsilon naught A over D, right? A over D. D is the same here and there. You didn't change D, but you did increase A to A1 plus A2. So equivalently, I can write this as epsilon naught A1 plus A2 over D. And that is epsilon naught A1 over D, which is C1, plus epsilon naught A2 over D, that's C2. You see that? So qualitatively, we can understand why by adding capacitors in parallel, we can increase the capacitance. Okay, and the way to understand that is to realize that all you're doing really is to increase the surface area of each plate. Okay, because you add more branches, you add more area. So that makes sense. Now, what if I have a third branch, C3, also in parallel with the first two? Well, the same idea applies, because now you're adding even one more area, A3, to the mix, right? So you can put even more charges, Q3, instead of just Q1 and Q2. Now you have to add Q1, Q2, and Q3 for the same potential difference, and therefore you just add C3. Just keep on adding depending on how many branches you have. If you have n branches, C1 plus C2 all the way to Cn. So this is how you find the equivalent capacitance of a whole bunch of capacitors in series. I'm sorry, in parallel. All you have to do is to add them up. Okay, you get a greater capacitance that way. Now next, let's add capacitors in series. That is a second common combination. Okay, it's different from connecting them in parallel. You start from point A, you go through the first capacitor, and then without branching out, you go through the second capacitor before reaching point B. Okay, you see, this is not the same as parallel connection. You don't branch out. You go from one, you go through one capacitor, and you do not branch out, you go through the second capacitor. They're connected in series. Okay, what is the equivalent capacitance of such a combination? In other words, if I replace this combination, this combo, with a single equivalent capacitor, what is the value of its capacitance? So let's see how we might calculate the equivalent capacitance in this case. Just like the previous case, what we're going to do is we're going to hook this up to a certain battery, which provides a certain potential difference between points A and B. Okay, so hook up to a battery. So the potential difference between this point and that point is V, which is supplied by the battery. Okay. Now, as a result, a negative charge will appear here and a positive charge will appear there. The battery only transports charges. It does not create a net charge. So what it does is that because here is a negative terminal, here's a positive terminal, it's going to transport some electrons from the positive terminal all the way to the negative terminal. So as a result, you can have some positive excess charge here, which we call Q. As a result, you get the equal amount of negative charge there, electrons, negative Q. That's all there is to it. Okay, now if this is Q, then how much charge is produced on this plate? Well, it has to be negative Q, okay? We have learned, when we studied parallel plate capacitor, that this Q and that Q must have the same magnitude and opposite sign, due to Gauss's law. And then as a result, what about Q here? Well, it's got to be positive Q for two reasons. One is, they must cancel out, just like that one. And secondly, if you look at this H-shaped structure, okay, this thing is really totally isolated from everybody else, right? No charge can go in and out of this H-shaped structure. So initially there was no charge, right? Before you put up the battery there was no charge. Now, all of a sudden, this side appears to have a negative charge, negative Q. Where does it come from? Well, it must come from the other side. So a certain amount of electrons move their way from here to there. The net charge of this H-shaped structure should remain zero, so you have a positive Q here, must have a negative Q there. So that's how it works. Everything works out. Okay, so you see here, in this case, because of the way it is connected, these two capacitors will now have the same amount of what? Charge. Okay, Q, negative Q, Q, negative Q. Unlike in the case of parallel connection, they had the same amount of voltage difference, but different Q. Now we have different voltage difference, but the same Q. Now what about the voltage difference? What about V1? V1 across these two plates and V2 across those two plates. Now suppose this is 0 volt and you hook up to a 12 volt battery, okay? So this point A, has positive 12 volts. After going through this capacitor, this 0 volt, let's say here we got 5 volts. Okay, so there's a 5 volt difference. And how do you go from 5 volts to 12 volts? You must go through a potential difference of how many? 7 volts, right? So you get 5 volts here, 7 volts there. So V1 would be, in this case, 7 volts. V2 would be 5 volts. You add them together, you get 12 volts. So, what can you say about the total potential difference V in terms of V1 and V2? Well, this potential difference is divided between these two capacitors, V1 and V2. It is clear, therefore, that V equals V1 plus V2, right? And yet, Q1 and Q2 are equal. Q1 and Q2 are equal. Okay, now, let's switch our attention to the equivalent capacitor. I'm going to hook up to the same exact battery, okay, which provides a potential difference V. How much charge would be here and how much charge would be there? Since I want an equivalent capacitance under the same voltage, I want this guy to carry the same amount of charge as this combo. That means that whether you take this combo or that single capacitor, I want point B to be connected to the same amount of negative charge as that point B, and point A, in this case, to be connected to the same amount of positive charge as that point A. Okay? But wait a minute, point A is connected to charge Q. That's not connected to here directly. It is only connected to the charges on this plate, so it's Q, right? So I want this to be Q as well, just like that. And I want that to be negative Q, right? Negative Q. So, in this case, V is the same as that, but on the other hand, Q is just Q1 and Q2. It's not Q1 plus Q2, okay? Because unlike the previous case, this Q and that Q, they're not linked to the same potential difference. the only charge that's directly connected to the positive terminal of the battery is this Q. And the only charge directly connected to the negative terminal of the battery is that Q. You don't add them up. Okay, with this knowledge, we are now able to find the equivalent resistance. Equivalent capacitance, C equivalent. Right? What is that equal to? Isn't that equal to Q over V, right? This Q. But that is Q over V1 plus V2. Right? Now, how do I work this out? What I'm going to do now is I'm going to divide everything of this expression by Q. So this is Q over Q, which is 1, V2 over Q. Q can be written either as Q1 or Q2. Okay, they're the same. So I can write this as Q1, this is Q2. Nothing changes, right? But wait a second, what is V1 over Q1? All I know is that for this capacitor, Q1 over V1 is equal to C1. Okay, Q1 over V1 equals C1 by definition. And for this guy, Q2 equals V2 equals C2, right? Now, I don't have Q1 over V1, I have V1 over Q1. So what do you think that is? That is not C1, but 1 over C1, right? So this first term is just 1 over C1. And the next one is just what? 1 over C2. Okay, now this looks a little awkward, so I'm going to flip the numerator and denominator, do the same thing for both sides. Then I have 1 over C equivalent equals 1 over C1 plus 1 over C2. Alright? Now this looks kind of funny. It's not C equivalent equals C1 plus C2. Rather, you add the reciprocals up. Okay, you add the reciprocals of all the capacitances in series. You will get the reciprocal of the equivalent C. Now, when you add the capacitors in a parallel connection, the final value of C equivalent is greater than each individual capacitor because you just add their capacitances up. On the other hand, if you put them in series, okay, things are a little different. You can see that C equivalent is less than the smaller of these two C's. Why? Because the reciprocal of C equivalent is greater than this reciprocal and that reciprocal because it's the sum of the two, right? And therefore C itself, C equivalent itself, is less than the smaller of the C1 and C2. You are getting the smallest capacitance out of these, even smaller than the smaller of the two. And what if you have 3 or 4 or 5 in series? Well, all you have to do really is just add V3, V4, and so on, right? So in the similar situation, just keep on adding, plus, 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 and this is how you find the equivalent capacitance of a whole bunch of capacitors connected in series. Okay, can we understand qualitatively why, by combining everything in series, we're getting a smaller capacitor, not a bigger one, unlike the case of a parallel plate? Connecting them in parallel. Well, we're going to again use the idea of a parallel plate capacitor. Let's say all these are, all these are parallel plate capacitors. Okay, for a parallel plate capacitor, the capacitance C equivalent is like epsilon naught A over D, right? A over D. Okay, suppose each of them has the same A this time, same area. But what about D? Okay, what about D? What's D? What's the definition of D? D, by definition, is the distance between the positive and the negative charged plates. Okay, now suppose you only have one capacitor. It's just distance between the positive and negative plate. That's it, right? But if you look at the case of two parallelly connected parallel plate capacitor, this distance we call it D1. Okay, so from here to there, you got D1. But then once you reach there, you're not quite at point B yet. You have to keep on going. Now, going from here to there, what happens to the potential? Well, this plate, and this wire, they form an equal potential body, right? So this point and that point have the exact same potential, and therefore, equivalently, I can shrink them from here to there as if this gap does not exist. I don't care how long the y is, okay? But once you reach this point is the same potential at that point, you're going to go through the same process again. You're going to decrease your voltage from here to there, going through the same another gap D2. So equivalently, the total distance between the positive plate and negative plate would be what? D1 plus D2. Okay, so now the reason why you can see we're getting a smaller capacitor is because you're increasing D. All right, the first case, in the parallel case, you were increasing A, which increased the capacitance, but now you're increasing D, the gap between the positive and negative terminal, and therefore equivalently you are decreasing the capacitance. That is the qualitative understanding why you're getting a smaller capacitor by connecting everything in series.